All right, so let's take a quick look at elimination reactions. These can happen under both basic and acidic conditions. Here we see the net reactions. So it's always useful to know where you're starting and ending up. An elimination reaction, as you see here in the first case, is driven by the addition of base and the removal of HBr, basically, to create an alkene. So you remove the bromine and the hydrogen. Eliminations always yield alkenes. Here under acidic conditions, we see the loss of water, the net loss of water. We can call that a dehydration. And same thing, however, you result in alkenes. Let's take a quick look at this reaction on the right. What we have is the addition of base and the mechanism of the E2 reaction where a proton is removed. So we see that bond-forming reaction right there with that arrow. The collapse of these electrons inward to create the double bond and the resulting displacement of the leaving group bromine, happening all at once and creating your alkene. Here's some dramatic footage of that same reaction. Deprotonation by the addition of the base, loss of the leaving group and the double bond forming. Let's take another quick look. Here comes the base. What you're going to see is that it's happening all at the same time, with all those bonds forming and breaking almost simultaneously. We call that a concerted reaction. All right, so when alkenes form, we have to keep in mind that they can have stereochemistry also. Another look at the elimination reaction. Here we have base. In E2 elimination, it would remove this proton. Notice these two electrons that comprise this bond are coming toward what is a delta positive or partially positive carbon here. Why is it partially positive? Because bromine is electronegative. So when those electrons come in, they force out bromine, which as we know is a good leaving group. We could propose this hypothetical transition state, and what you're seeing here is the formation and breaking of all these bonds with the dashed or dotted lines, I should say. So happening all at once, a concerted mechanism, which is just like in SN2, being as far as being a concerted mechanism. Formation of the alkene. Some old knowledge, hopefully not forgotten. If I draw the starting material of this reaction as a chair conformation, we see that the bromine and the hydrogen are both axial. This could flip, of course, to where they're both equatorial, but the elimination reaction hinges on this orientation, and I'll draw the arrows again this way. We call the arrangement of this hydrogen and this bromine as anti-periplanar or trans-periplanar. Remember Newman projections. There's our hydrogen, there's our bromine. So Newman projections can help us analyze the course of elimination reactions and sometimes help us determine the stereochemistry of the resulting product, which in this case is an alkene, without any alternate stereochemistry in that case. There's also an elimination reaction that is unimolecular. So where the E2 elimination is similar to SN2 in that the two materials come together to initiate the reaction, the base and the starting material. Elimination, that's E1, results from dissociation of the bromine to give you a tertiary carbocation. So this is really the same as the first step of SN1 reactions. So SN1 and E1 reactions have the exact same first step. leading to stable tertiary carbocations, sometimes secondary. Now we have what can act as a base, like ethanol here. The lone pair electrons on oxygen can remove this proton. These electrons will readily go toward a plus charge and result in our alkene product. Notice you can remove any of these neighboring protons and achieve the same result. If you remove these lower ones, you end up with the alkene down here, but as it turns out, these molecules are the same. That might not always be the case. You might remove different protons and end up with different products. We see Zaitsev's rule that can be applied where more than one alkene product is possible. So if we start with this alkyl halide, under these basic conditions, sodium ethoxide, typically in ethanol solution from which it's created, in base, we see that we could remove any of the hydrogens implied here, or here, or here, resulting, in this case, in two possible products, because removal of protons here and here both result in this material. Take a look at that for a few minutes to convince yourself that that's true. Zaitsev's rule says that the more substituted alkene is produced in higher amounts. Now, in many cases in chemistry, if you get the less substituted alkene under some conditions, I'll refer you to the book on that, we would call that the Hoffman product, the Hoffman elimination product. Okay, so under acidic conditions, we saw above the net reaction where water can be removed. So if you start with an alcohol like this, and it is protonated in acid solution as we see here, then we have, remember, our good old great leaving group. Great leaving group. So at this point, you can have E2 elimination, for example, where a proton here is removed. These electrons fold in and kick off that great leaving group, producing E and Z isomers of this alkene. Probably the E is going to be predominating because E alkenes are typically lower in energy, more stable. So don't forget that there's the possibility of E and Z isomers anytime you produce an alkene. Here's another dehydration reaction. Protonation. There'd be an inner arrow here that I'm not drawing. Here's our protonated material. If you need to, draw this all out. I saw people still having trouble with kind of knowing where implied atoms are and where electrons are. Remember, if you draw this all out, you can see everything. So with addition of a base, or maybe just water in this case, can act as our base, because we're in acidic conditions, right? So you're not going to really have a base. You can have removal, for example, of these one of those protons, and kick off that leaving group. And that would result, in fact, in product 2, shown down here. Removal of any of these other protons will result in products 1 and or 3. Convince yourselves, though, that 1 and 3 are the same in the structures. 2 is your more substituted alkene, your Zaitsev product, and probably favored in this reaction. So we have reading assignments. I think the Klein reading is actually better in this case, and then you have suggested practice problems, and the assignment is posted.